Hi, my name is Arya, and my project aims to develop and test an intelligent and affordable autonomous irrigation system specifically intended for water conservation in developing nations. In my recent trips to India to visit my family, I was shocked to see massive fields of land left barren from water shortage, which I later discovered is a direct effect of agricultural water wastage that affects an estimated 2.8 billion people worldwide. This experience inspired me to leverage my passion for engineering and computer science to help mitigate this problem. My first step was proving the correlation between ideal irrigation volume and crop color, which I interpreted as an accessible metric of crop health. The data collected by my constructed mechanism showed overwhelmingly positive results in increased irrigation efficiency. My secondary irrigation system, which made up my current year's research project, leverages a network of hardware components and a semi-supervised recurrent neural network to accomplish my engineering goals. I'll dive into the technical details for each component later in this presentation. The secondary system comprises three distinct components, each serving an integral function in the irrigation network's success. The irrigation micropiece, field analysis drone, and neural network server communicate through internal LAN requests and leverage a unique usage of RFID to map relative distance to absolute location. The machine learning component of the project is responsible for making predictions for the ideal irrigation volume for individual crops. A semi-supervised recurrent neural network allows the model to identify correlations between independent data points and resulting crop health without requiring extensive datasets. Long short-term memory units were found to have better accuracy, and its bidirectional analysis of past and present iterations allows better context analysis of the data. To extract quantitative information from each crop image, k-means clustering algorithms are used to yield an HSV-adjusted color as a dependent variable parameter. Underneath the neural network, there are four hidden layers that utilize arithmetic, sigmoid, and hyperbolic tangent functions to manipulate the dataset to adjust a dynamic cell state. This filtered cell state gives an increasingly accurate iteration output, representing the ideal irrigation volume. The irrigation micropiece is responsible for adjusting the irrigation volume for each individual crop. After receiving instructions from the neural network iteration output, the servomotor adjusts the truncated cylinder within a tube punctured through irrigation pipes to control the dynamic irrigation volume. An important quality of the irrigation micropiece is power self-sufficiency, which means that the power generated from the water flow eliminates the need for an external power source. EMF calculations of power production versus consumption yield a 25.8% excess margin, which can be visualized in the graph. The final component of the irrigation network is a field analysis drone, which collects environmental data and crop images for analysis by the neural network. A Raspberry Pi-based circuit is responsible for data collection, communication, and controlling the motion of the quadcopter-based drone. Finally, I tested the accuracy of the neural network's model predictions. Because my project takes a novel approach to analyzing environmental and crop data, there is no cumulative dataset that would fulfill my desired parameters. To solve this problem, I meshed multiple specialized datasets into a single, scalable dataset, which enables a more seamless transition to implementation. The graph shows the progression of loss and accuracy as the model progresses through a growth cycle in 4 nations. To measure success, I used multiple machine learning metrics that provide both an absolute accuracy score and binary classification accuracy rate. The results indicated that affording the model a margin of error when adjusting irrigation volume proved to be the most successful in analyzing high variability datasets. Overall, all measured statistics showed the system's overwhelming effectiveness in minimizing irrigation resource wastage. By operating as a low-cost, high-impact system that enables farmers in developing nations to affordably improve their infrastructure, this project has the potential to significantly improve the global water crisis at the root of its problems. I recently self-filed and published a utility patent enclosing the work performed, and I am excited to continue working towards making a real-world positive impact with my project. Thank you.